We will discuss mining spatial colocation patterns. What is spatial colocation pattern? Usually, a group of spatial features or events can be frequently collocated in the same region. For example, West Nile virus may often occur in the regions with a poor mosquito control and the presence of birds. So if we can find such patterns, we may have better way to control the spread of the virus. Let's look at the example on the right. So we have A, B, C, D as four types of objects. You can think A could be West Nile virus, spreading region. B could be some mosquito region, or C could be in some cities. D could be the presence of birds, something. Okay. Then we use the edges, means they are collocated. For example, 3, 6, 17 are collocated. We use edge, link them together. And 4, 7, 10, 16 are collocated together. We use the edges, linking them together. Okay, like 2, 9 could be collocated, but on the other hand, 2, 14, 18, 11, and 15, these are collocated regions. Okay. Then we may be able to find row set. The row set means this. Okay, if we want to find A, B, C, D, how many objects are collocated together as A, B, C, D for types? We may be able to find 4, 7, 10, 16 are collocated, and 2, 11, 14, 15 are collocated, or 8, 11, 14, 15 are collocated. That means A, B, C, D, we may find actually 3 instances they are collocated. That's their row set. On the other hand, A, B may be a little more. For example, 5, 13 is collocated, 7, 10 is collocated. So we may find more, instances. Then we may get a collocation rule like this. If pattern A is collocated, whether pattern B are also collocated, we may find this conditional probability of the collocation patterns. That means if we want to find AB may imply CD. That means if AB are collocated, likely CD will be collocated with certain, probability. Then we need to compute the pattern A at what condition and how many cases when A is there and AB is also there. That means actually AB, the cases essentially is the case. You can find A and in the row AB row set. Okay. Essentially what we need to calculate is ABCD is a row set. You probably can see there are 3 such cases ABCD together, but there are 4 cases AB together. So the condition, if you find AB, then you find a CD are collocated, then the condition actually 3 over 4 is 75%. That means the conditional probability for this rule is 75%. Then the interesting thing is, can we find such collocation patterns and rules automatically and efficiently? Okay. So let's see how we can derive efficient algorithm to find them. Okay. To find efficient algorithms, we first introduce another concept called participation ratio. Okay. That means that the feature F is participating in this pattern C. What's the probability? Okay. So for example, A participating in ABCD, you can see A is a red one. We have 1, 2, 3, 4, 5 cases you find A. But every time we find A, we can find ABCD. There are only 2 such cases, like 7 and 14. That's why we get a 2 over 5 is the participation ratio. Similarly, if you want to find D participating in ABCD. D actually is the blue circle. You can see there are only 2 blue circles, but both of them is completely participating in this ABCD pattern. That simply says you get cases 2 over 2 is 100%. Then we may derive an interesting property called monotonicity property of participation ratio. Okay, that means suppose we have C and C prime as 2 collocation patterns, but C prime is a subset of C. Okay. Then for every feature F, if feature is participating in C prime, okay, then the probability will be higher than participating in a superset. This is quite easily can be easily understood because you can think about this. If A participating in AB, okay, then the chance is higher than A participating in ABCD, because every time when AB occurs, ABCD also will be there. When ABCD occurs, AB will also be there. That's why when F participating in C, for sure the probability or the participation ratio will be higher than participating in its superset. So based on these monotonicity, we can work out an a priori-like algorithm to efficient mine collocation patterns. Let's give such an example. Suppose minimum feature support is rewritten as sigma, and the minimum participation ratio is rewritten as rho. Then we start from a set of single feature patterns. If they are frequent, that means if their support is no less than sigma, okay, then we can keep using a priori like a principle to find their pairs. That means from the single feature pattern, try to find 2 feature patterns, 3 feature patterns, grow up to size k. Anytime we can stop if the pattern is not frequent anymore, because once it's not frequent, its super pattern will not be frequent. This is simply based on the a priori principle. Then based on these participation ratio monotonicity, we will be able to find all the super patterns of a single feature or the multiple features. Suppose we get a feature is P, we want to find its super feature, okay, or super pattern. And we know we can get a little bigger super pattern to see whether it's greater than rho. Anytime if it's not greater than rho, its super pattern will not need to be examined because they cannot be bigger than rho anymore. So based on this a priori principle, we can easily work out efficient algorithms. So that's the trick, or that's the interestingness. If we can find a monotonicity pattern, we will be able to work out, a priori-like efficient processing algorithm.